Lecture 10 covers sections 3.7 and 3.10. At the end of today's lecture, you should be able to calculate the change of internal energy through the formulation of constant volume specific heat. For us to begin, let us recall our conservation of energy equation. Our COE states that the change of our energy is equal to our heat supplied less our work done. And we have formulated how to solve for delta W for any process through the use of our polytropic index N. And we also recall that our total energy, E, is the sum of our internal, kinetic, and potential energies. If we consider a system where there is no change of our kinetic or potential energies, we say du, the change of our internal energy, is equal to delta Q, our heat supplied, less delta W, our work done. Now, if we rearrange our conservation of energy equation, we can say our heat supplied going from state 1 to state 2 is equal to du plus delta W. Now, if we recall our definition of work, delta W is equal to PdV. Thus, our heat supplied going from state 1 to state 2 is equal to change of our internal energy plus PdV. Our heat input or output of the system can easily be determined from our change of internal energy, du, and the work done onto or by our system, PdV. Now, if we consider a single, homogeneous phase, the specific heat, defined by variable C, is the amount of heat required per unit mass to raise our temperature 1 degree. And this concept goes back to 1761, when Joseph Black discovered the latent heat of materials. That is, when ice melts, it does not cause the temperature to increase, rather there's an increase of the amount of liquid that forms. This concept is very similar to a vapor dome. We have a constant temperature process as we move from a saturated liquid to a saturated vapor state. Now, if we take our conservation of energy equation for a quasi-equilibrium process, Q, going from state 1 to state 2, is equal to du plus PdV, and if our volume is constant between states 1 and 2, delta Q is equal to du. Thus, we can find our constant volume specific heat, C sub 4 all, as the amount of heat required per unit mass to raise our temperature by 1 degree. That is, C sub 4 all is equal to 1 per m, delta Q per delta T. And our subscript V indicates it was for a constant volume process. And if we make the substitution from our conservation of energy equation, where delta Q is equal to du, we have delta U per delta T. Now, since U does not depend upon path, we can use a full derivative, d. That is, our constant volume specific heat is equal to a change of internal energy per our change of temperature. We can arrive at the same solution considering U being a function of both T and our specific volume. And if we apply our chain rule, we have du is equal to del U, del T, dt, plus del U, del V, dV. For a constant volume process, our change of our specific volume is equal to 0. That is, our second term on the right-hand side drops out. Now, recalling our conservation of energy, in our specific terms, our specific internal energy is equal to our specific heat supplied less our specific work done, or du is equal to delta Q minus P d nu. The second term on the right-hand side is once again 0 for a constant volume process, so del Q is equal to du, which would be equal to del U per del T dt. Or if we rearrange this, del U per del T would be equal to del Q per del T, and thus we arrive at the same solution. Now, it is evident the increase in our specific energy is due to heat transference. Therefore, by definition, our specific heat is equal to a change of internal energy per our change of temperature. Constant volume is a misnomer. Although we considered a constant volume process in the formulation of our constant volume specific heat, our constant volume specific heat is a thermodynamic property that is defined in terms of a derivative of a variable with respect to temperature, du dt, rather than a quantity related to our heat transferred, delta Q. Since the derivatives are defined at any point in a quasi-equilibrium process, our constant volume specific heat is a thermodynamic property of our substance, and it only depends upon the state, and not our path. That is, our specific internal energy is a state or point variable. Same with our temperature. There is no path dependence in determining our specific internal energy or temperature. Our constant volume specific heat can be used whenever we are interested in a change of internal energy. That is, du is equal to Cv dt. It is noted that the process does not have to be constant volume for us to use constant volume specific heat. Note the equation in our box uses full derivatives. It does not depend upon path. Thus, we can use our constant volume specific heat for processes that are not constant volume.